In this video, we'll define entropy in terms of thermodynamic properties. We'll look at the change of entropy for physical processes, talk about the second law of thermodynamics, and look at the effect of temperature on the spontaneity of a process. We mentioned before that the entropy is a function of the positional probability and Boltzmann's constant. And we also mentioned that this omega can be very huge for something containing a realistic number of molecules, but we can approximate the change in entropy by looking at the heat at a given temperature. And we're not going to worry about the derivation of this, but you can look in the textbook if you'd like to see it. So the typical units for entropy are going to be joules per Kelvin. So the change of entropy for any process is always going to be the reversible heat over the temperature. So even though we built this up for an isothermal expansion, this will be true for any process, whether it's isothermal or not. So here we have a definition for what the reversible heat is for an isothermal process, and that's this nRT ln V final over V initial. And so delta S for an isothermal process will be equal to this equation down here. Different processes are going to have different reversible heats, and so we'll have a different expression for delta S. You don't need to memorize any of these equations. The important part is just knowing which equation to use depending on what circumstances you're under. So if temperature is constant, this is isothermal, and this is the equation we've already looked at. If we are melting, so this is going to be another constant temperature process, but not of a gas. So this is if we have a solid going to a liquid, then the reversible heat is the number of moles of that solid times its heat of fusion. And then for the entropy, it's that expression divided by the melting temperature. So for water, this would be the heat of fusion. For ice, and this would be the melting point of 273 K. Something else to keep track of, all of the T's on all of these expressions, you'll want to use Kelvin. If it's boiling, this is very similar to melting, except now we're going from a liquid to a gas. And this is just going to be the moles of the liquid times the heat of vaporization divided by the boiling point of that liquid. A couple more processes. So if we have a gas with constant volume instead of constant temperature, this becomes the expression for change in entropy. And if it's at constant pressure, this becomes our expression for the change in entropy. So let's look at how we might apply some of these equations by looking at a phase change in cooling for water. So we have 2 moles of liquid water at 0 degrees Celsius. What we want to do is freeze this water, so go from liquid to solid. And then once it's ice, we want to cool the ice to minus 15. We're going to do all of this at a constant pressure, and we've been given the heat capacity for the ice, the heat of fusion, and that we're starting with 2 moles. When we're doing these types of phase change problems, you can see that we actually have more than one circumstance. So first we're going from liquid water to solid water at constant T. And then next we're going from solid water at 0 degrees Celsius to solid water at 15 degrees lower than that. So since it's a state function to find the delta S for this process, we can just add together the delta S for the 2 individual processes. So for step 1, freezing water, we're going to use the delta S equals N delta H fusion divided by T. Why do we have the minus sign? Well, remember that equation was for melting water, so since we're going the other way, we will change the sign of this. And then for the second step, we want to cool the ice at constant pressure. So I'll use the constant pressure equation to find that delta S. So for the first step, it's going to be negative 2 moles times the given heat of fusion divided by the temperature, and we get negative 44.18 joules per Kelvin. For step 2, this is our 2 moles times the heat capacity times the log of the 2 temperatures, and this will be the final over the initial, and that's equal to negative 4.24 joules per Kelvin. When we combine these two together, we get negative 48.4 joules per Kelvin as the entropy for this process. Here's a visual depiction of the phase change versus temperature. So note we got a negative value for the entropy. And remember, entropy is a measure of disorder, so negative entropy means that we're getting a more ordered system. And so if you look at this process where we had a liquid that was freezing, we were clearly getting more order there, and as we cooled it down, there was less vibration of the water molecules, and hence an even lower entropy. If you had a more complicated problem with multiple transitions, so say you had a gas at a really high temperature, you cooled it down until it started to condense, and then cooled it down until it froze, and then cooled it down some more, you'd actually use a separate equation for each component of this phase change diagram. So it's useful when calculating these entropies, or even an enthalpy of a phase change, to keep track of the different steps so you can keep track of which equation you want to use. Okay, so next we're going to move to talk about the second law of thermodynamics. So the second law of thermodynamics relates entropy to spontaneity. When we were going over our initial idea of a spontaneous process and just looking at the probability, we saw that a spontaneous process is going to tend to be the one where we end up with the most probable state. And since that was aligned with more degrees of freedom, this is also tied in to the concept of entropy. And the second law is going to state that the entropy of the universe is going to tend towards this most evenly distributed or most highly disordered state. And the delta S of the universe can always be defined as the delta S of the system. So this will be the specific equation that we're looking at, plus the delta S of the surroundings, and this is literally everything else. So if the system was a block of melting ice, the surroundings would be the room around it, the table it's on, the house that it's in, the planet that the house is on, and everything else except for that one little block of ice. So because the entropy of the universe is strictly increasing, that means that if we have some reaction where the delta S of the universe will be zero, that means it's going to happen in our universe. So that's what's going to make a spontaneous process. Anything where the delta S universe is greater than zero will be spontaneous. If it's less than zero, that means that it won't actually happen in our universe, and this is a non-spontaneous process. And in the rare event that the delta S of the universe is equal to zero, this would be a completely reversible process. And we saw these are rare, but we do have a few exceptions, such as reactions going back and forth at equilibrium, or something going back and forth for melting and freezing at its normal melting point. So we can use these concepts a little bit to just talk qualitatively about the sign of delta S. So let's say we are outside and the temperature is minus 15 degrees Celsius. And we know that if we have some water outside at minus 15 degrees Celsius, the water is going to freeze. So if the system is just the water, what is the delta S for the water when we're outdoors and the water is freezing? Right, and so for this, the delta S of the system is negative. And so this is important to note that when you're looking at the delta S of the system, you want to look at transformations and order of the system. So since we have a liquid going to a solid, this is becoming more ordered or less degrees of freedom, and hence delta S is getting smaller. Okay, so water is freezing at minus 15 degrees Celsius outside. What do we think the delta S for the surroundings would be? And that delta S is going to be greater than zero. Why? Well, in this case, heat is going to be released into the surroundings. And to think about that, we could write this equation. So we have H2O as a liquid, going to H2O as a solid. And there's several ways to think about this, but let's talk about this in terms of how we know temperature affects water. So we know that if we add heat to solid water, it'll tend to melt. And with that logic, heat can be written as a product of this reaction. And so that means when we freeze water, go the other way, heat has to be released into the surroundings. So when we're thinking about the delta S of the surroundings, if the surroundings gain heat, then this will be greater than zero. And if they lose heat, this will be less than zero. And we can think about this as the dispersion of the energy from the water is increasing the entropy or the disorder of the surroundings. Okay, so last question, when we observe water freeze at minus 15 degrees Celsius, what is the delta S for the whole entire universe? And in this case, it's just going to be greater than 0. While this is a big concept, thinking about the whole universe, finding the delta S for the universe for a system that we can observe is actually relatively easy. Because of the second law of thermodynamics, we know that if it's spontaneous, the delta S of the universe has to be greater than 0. So since it happened, we know that this is greater than 0. You all know that water will freeze at minus 15°C, and so intuitively you know that this is a spontaneous process and that the entropy is positive. If it won't happen or it's non-spontaneous, then delta S of the universe is going to be less than 0, and if we have something at equilibrium, it's equal to 0. So to recap, if it's spontaneous, delta S of the universe has to be positive, and we know it's spontaneous because it happened. So as an overview, when looking at the delta S of the system, you want to consider the order and transitions. For the surroundings, you want to consider heat. And for the universe, you just want to consider whether or not it happened. Okay, so let's look a little more about the role of heat and temperature in spontaneity and entropy. So we just saw that the delta S of the universe can be spontaneous, even if the delta S of the system is less than 0. The whole universe can be greater than 0, but of course this is only going to be true under certain conditions. So what conditions would this be true? Well, we can think, is water always going to be a solid? And no, it's not. We know that water is a liquid if it's above freezing. And this is telling us that temperature is going to be important to spontaneity. So we can think of it this way. We have the delta S of the universe, the delta S of the system, and the delta S of the surroundings. And the delta S of the universe will be positive even if the system is negative, as long as the delta S of the surroundings is an even bigger positive. If the delta S of the system is negative, but the delta S of the surroundings is a very small positive, then the delta S of the universe will still remain negative, and it won't be a spontaneous process. And this is what we can see happening with water. The relative amount of heat that's being exchanged depends on the external temperature, and hence the effect of the delta S of the universe during this phase change.